So just so we're all on the same page, if we look at an electric powertrain, at some level we have an inverter, or excuse me, a battery or a power source that's supplying a DC power. That DC power is going into an inverter. This inverter is turning on and off a series of switches in the tens of kilohertz rate, which is really turning on magnets at tens of kilohertz, which those magnets being turned on and off at tens of kilohertz create torque and rotational speed. And that rotational speed then goes into some sort of mechanical output. And I've got a propeller on the board, um, but it could also be an axle or a series of axles or a gearbox. Uh, and I think the really important thing here is that we have this high frequency inverter that's in the tens of kilohertz, but we also have a rotating machine. And this rotating machine has kind of the traditional NV qualities at orders that are a function of rotational speed. So we have really two elements. We have a magnetic element and this rotational element, and those two things make for some really interesting interactions. So we'll really jump into the meat of it. Um, so the first topic we'll cover is motor construction in regards to vibration. So where I'll start with this is that electric machines are excited by typically three-phase or some multiple series of phases electric power. And if I pull up my little laser pointer, if we follow this three-phase power, torque is actually going to follow the envelope of the peak current. So we end up getting this torque that's got a sinusoidal element, that's got this little ripple to it. And this ripple is really just a function of the excitation. So it's fundamentally there. Now, you might say, Mitch, why does this have to do with construction? Because the first thing we'll talk about is winding. Initially, we have this torque that's following the envelope of our currents. And we can do a little bit to control this with the winding of the machine. So you'll look at my pole of a machine here. I've got the blue for phase A, red for phase B, yellow for phase C. We can wind these in different ways to minimize this ripple, but it's always going to be there in some capacity. The next thing is that we have the physical machine itself. Now, especially in the automotive or aerospace world, a large number of our machines are permanent magnet. And the green rotor here, I have my permanent magnets. There's two of them at an angle. Well, these permanent magnets want to stick to the stator. So the stator is this gray iron. And these windings have these little tooth slots. And each magnet wants to stick to this iron. And if you've ever grabbed a machine and a permanent magnet machine and tried to twist the shaft, you get this little cogging torque. Is everybody muted? So you get this cogging torque, and we feel this in the stationary, but this is also happening while it's spinning, and this is what we refer to as torque ripple. Now, the torque that we're creating with the excitation and the torque that's coming from this ripple, when we input current into the machine, we get a force that causes torque in the rotational space. We also get a tangential torque that's exciting the housing. And this is going to be the source of a lot of vibration and subsequent noise. And what I've found that's really interesting, and I've been having several discussions about with customers, is that we can use this excitation, and we can use this permanent magnet ripple and this iron ripple to actually create noise and vibration, and use this for sound design. And I'll touch some more on this, but we're really looking to merge these two things for a good experience, but we also want to minimize them in other circumstances for durability and fatigue. So construction has a lot to do with torque ripple and then subsequently noise and vibration. As I mentioned, we also have the inverter. So the inverter is turning on and off this DC power to create AC. And one of the most typical ways we do this is with what we call a PWM, so a pulse width modulated excitation. And in the top graph, I have an example of this PWM. And we can see that the black squares, that's my voltage. It's on for a period, off for a period, on for a period, off for a period. And we actually get these variable pulse widths that for a given rotational speed have a variety of frequencies. And if you've ever looked at a spectral graph of an inverter, which we'll look at in a little bit, you can actually see all these kind of side bands and fan blades. But what we're trying to create is a current that's got this sinusoidal look. so we have this really high frequency thing creating this smooth AC wave. So in the PWM, we end up having noise and vibration that's caused by these discrete voltage pulses, which are creating current pulses, which are creating magnetic pulses, which are creating torque, which is creating NV. And this is the best case scenario because we have a very sinusoidal current. Um, on the other hand, there's a variety of control operations that can be used. And many of these control operations have asynchronous pulses of voltage or current, or they have non-sinusoidal currents, so they can throw a lot of harmonics into a system. And the example I have on the screen here is I have in blue the voltage from what we would call a six-step operation. So this is a low frequency on-off discrete pulses. And we can see that the current in red it's a sinusoidal shape, but it's got these very jagged edges. And this is current harmonics. And then in the pink, I have my torque. And granted, this is one of three phases, so this torque's going to have a higher frequency torque ripple than we see here. But we can see while that switches on in blue, we have this current that's dipping and rising, and we have a torque that's subsequently rising. And these are all things in torque that are going to excite the housing. So this really is a large electromechanical problem. And each control type is going to have its own kind of torque characteristic and its own noise and vibration characteristic because of where that excitation is going. So to go a little further, and this will become more evident in some of my future slides, but the reason we use three-phase AC excitation is that we use sinusoidal excitation to eliminate the 2N harmonics, so the second, fourth, sixth. We use three phases or functions of three, so 6, 9 phases, to create a balanced load. And what we find is that we get a fundamental, so a first harmonic that is at 0, 120, 240 degrees. And that creates positive rotation, or we'll call it clockwise rotation. The third harmonics are eliminated, so we get no rotation. But what's very interesting is this fifth. The fifth harmonic actually ends up creating negative torque or counterclockwise rotation. So this is something we really have to watch out for. This fifth, 11th, these harmonics that create negative rotation. And I promise that this will have some meaning in the future. So characterizing NV for electric machines. Just a quick, nothing's free. So this is my quick pitch. We have a product called eDrive. eDrive is really meant to streamline and simplify the collection of electromechanical signals. What that means is we can measure voltage, current, power very accurately, but we can also measure noise, vibration, torque, speed, temperature to give you a full system level view. We're a chassis-based system, so we can expand out to fit your needs for complex or simple systems. And we record all the data so you can actually audit your test and validate your results. And again, we like to think of ourselves as a full system provider, so we're sensors, acquisition, and software. And these products will be used throughout the rest of the presentation. So, inverter voltage influence on mechanical torque. So, torque has a frequency component, and a lot of people end up looking at filtered torque and they don't realize this. But if we look at a machine running under two different circumstances, and what I have on the board in the left is I have voltage, current, and torque for a machine under a PWM sinusoidal excitation. And we have a 13.5 K frequency voltage. We have a nice sinusoidal current, and we can see in our torque a ripple element, and actually that slow speed ripple's likely from the dynamometer. We've got a ripple imposed on it that has some frequency content. That's probably construction, slotting effects, excitation. And this will have an NV element, a noise and vibration element. But what becomes really interesting is when we switch to what we call a six-step operation. And we go from that 13.5 kilohertz frequency to a 600 hertz frequency in voltage. And we can see that just much more discrete on-offs. If we look at our current, we can see that jagged current again, and this is the same one I showed earlier. Try to repeat data sets so we become familiar with them. And what we see is in the transition period, when we make that switch, we get this really nasty torque. But it has frequency and amplitude, so it's not noise. This is reality. And there's actual negative swings, and then it settles out, and we still have this really, really nasty torque. Um, and even these small peaks can excite resonances. So um, this is really gnarly. And it's all inverter controlled. The machine didn't change. This is purely controlled by the inverter, so controlled by the electrics and magnetics. Now, again, I think this is time where we step into the frequency domain and we start thinking like NV people. So we can actually run an FFT of that. And if we do an FFT of our current and our torque, we can see in blue is the PWM operation for both scenarios. And we get this, fundamental frequency and current right around 100 hertz. And we get this fundamental frequency in torque that's right around 50 hertz. So it's a 4-pole machine. We can see that for the fundamental and torque, our red and our blue, so our 6-step and our PWM, are almost identical. So that's cool. That gives us some confidence that our dyno is at least consistent. But when we start looking at the torque FFT, we can see a little spike in blue, so in the PWM at 200 hertz. But then in the red, in the 6-step, we have this just gigantic spike, which is almost 4 Newton meters worth of content at 200 hertz. So that's incredible, and that we believe is attributed to the poles in this circumstance because it's a 4-pole machine. We see a really big step in the 5th harmonic. Now, if we remember back to that slide I showed, the 5th harmonic is actually a reverse torque. So we have some 5th harmonic content in the blue, but we have about 2 Newton meters worth in the PWM, or excuse me, in the 6-step. We have a little peak here at 400 hertz, which is likely due to construction of the machine. And we have a big peak here out at 600 hertz. And if we remember, I said that the torque follows the envelope of the ripple, or the envelope of the peak current. That's what this is. That's 6-step operation, 100 hertz, 600 hertz switching. We get this big peak out at 600 hertz. So this is pretty wild that we get these huge influences of torque from the excitation, and this is really attributed to that torque ripple. And again, this is all going to be resonated out into noise and vibration at some level. So let's start looking at some accelerometers. So current and vibration can really be looked at side by side in a lot of circumstances. So torque sensors do have a limited bandwidth. The HBM torque sensors go up to 6 kilohertz. So for things beyond that, for characterizing torque, but also noise and vibration, accelerometers and microphones are very useful. And if I take vibration and current from a steady state operation of a machine, I think we were operating at 3K RPM. We can see highlighted in the blue, we've got some harmonics from our fundamental. So these might be referred to as orders. So we have some orders coming from the fundamental. And the current and the vibration don't have all of the same peaks, but the peaks and vibration are really closely related to the peaks and current. But then where it becomes really interesting is when we look at the inverter switching. So in the green, right around 10 kilohertz, we have a bunch of peaks in our vibration, and those can be tracked really closely back to these peaks in current. But we can see that the peaks in current have a big peak at 10 kilohertz and then smaller sidebands out, whereas the peaks in vibration have pretty big peaks in the sidebands. And this is because those are likely exciting resonances in the machine. So even a small amount of current can excite a big resonance in the structure. So that I think is a really interesting takeaway, is that while current and vibration are correlated, there's a transfer function in there that can either amplify or diminish the amount of vibration. And then this specific machine was a wound field machine, so there's a field winding. And if we look at the peaks here, it looks like these two peaks are really closely correlated at 20 kilohertz. But if you look at the peak values, so the actual frequency values, we find that the field switching frequency and the vibration are not necessarily at the exact same frequency, which really threw us off, because there's obviously some causality there, but they're not directly correlated. So we really cannot make the assumption that current and vibration are directly correlated. There's definitely something causing both of these, but there's some sort of transfer function or some sort of resonated vibration going on that's making these slightly different. So we really do need the whole picture. We need the voltage, the current, the vibration to even start to understand why some of these problems are happening. And if we had uncorrelated data, it would really be a nightmare to try to piece this story together. Um, on the more basic end, and this is probably the most boring slide I have, unfortunately, um, is that loading really does influence the frequency spectra of vibration. So I have a machine, again, steady state at 3,000 RPM at three different loading states. So in the green, I have 0 Newton meter loading. In the blue, I have 13 Newton meter loading. And in the red, I have 26 Newton meter loading. And if we look at the current spectra, we can see that with increased current, we have increased spectra. No surprise there. In the vibration, with increased loading, we have increased vibration spectra. And there are some areas where maybe the green is peaking or the blue is peaking, but overall the peaks are higher at the highest loading. Um, so not super interesting, but I think it's a really good point to make that often these things do increase with loading. Um, and what we really do need to watch out for is this is just the machine, but if there's a gearbox or a transmission, these could excite different resonances in the gearbox. So you could see peaks at certain loadings that are worse than others. Or there could be different control types that have different influences on the peak. So again, really important to watch out for all these different phenomena and monitor the whole system because this is a system level problem. For the electrical guys in the room, I'm going to present spectral plots because they're really useful in the NV world, and we can use them for how we use our electrical signals as well. So what a spectral plot is we have RPM in the X. So we took a machine, we ramped it from 0 to a certain speed, hold at the speed for a little bit, and then ramp from speed to 0 all in one run. And this could be over a various period of time. You record the frequency of a vibration or a current for that sweep. And on the Y, you plot what speed you had. On the X, you plot frequency, so the frequency of interest. And then in the contour plot, you put the presence of that frequency. So the brightest lines are going to have the strongest presence of frequency. And what we can see in vibration is we get these lines where as speed increases, a frequency increases, and we call these orders. In current, we have almost the exact same thing. So we have our fundamental, which is really bright, and then we have our other orders or our other frequencies, or harmonics, I guess we'd call them in current. And I've just highlighted a red line where I've got the fifth harmonic in current and then the fifth harmonic in vibration, and this just gives us a really nice way to compare where is something coming from. Is this vibration caused by this current? And what we can see as well is vertical lines in vibration are resonant points. And we do have similar things in the current as well. And I just want to introduce this. We'll talk about more of these in the examples. So the question we're all dying to know, why measure both? As these two worlds are becoming closer and closer together, because we need, this inverter has such a big influence on vibration, and we can control the inverter and change parameters very quickly. We can start looking at reducing costs by having a single test to do both. Having one test stand where we can instrument for NV and for controls can just really be a capital cost reduction as we bring up new labs. As we're creating new test cells for electrification, we can do both in one place with one piece of instrumentation. Faster communication between groups. It seems like right now there's a big race for everybody to get new vehicles out. We all have pressure to develop things quickly. If you can reduce communication time, so take data sets that have noise and vibration, or set parameters and noise for the electrical groups, or set parameters and efficiency for the noise groups, we can develop things much more quickly, and we can have easier communication to simulation. if you can just take one data set, feed it into a vehicle simulator, and jury test it, that's pretty cool. Sound design. As we start designing for sound, noise and vibration and electrical guys need to become best friends. Fatigue characterization. Since the inverter has such a big influence on NV, you can start feeding these data sets into solvers and understanding the fatigue from things like voltage or current. Failure testing, obviously, when something goes wrong, you want to have the root cause. If that root cause is an inverter, you want to know about it. Resonance tracking, and then these things can be really useful for end-of-line characterization. And the image I have on the board is pretty simple. It's a ramp up in a propeller test where we have voltage and current, we ramped up. We have a load cell where you can see the force caused by that propeller ramps up with the voltage and current, and the vibration follows it. The power level dips down, so the load dips down, the vibration dips down. You know, there's a lot of insight that can just be had from what state is my voltage and current in, what is my mechanical state, and how much am I vibrating or how much noise am I making. Seems intuitive, but seeing it all in one place lets us make decisions quickly. So our case study. We have we partnered with the University of Illinois, so the Illinois Institute of Technology, and they have a three-phase traction motor. It's permanent magnet and wound field, so we have an extra variable. We can change the field flux. It's an 8-pole machine. We ran a series of tests. One of them was a point-by-point traditional efficiency map. The other one was a ramps test that we get those spectral plots from. And we measured the quantities for the inverter voltage and current, torque speed, vibration, and noise. And what I have on the screen, this is a really cool tool our Brule and Care friends have. It's an acoustic camera, so it's an array of microphones with a video camera, and you point it at the electric machine, which is featured here, and it records the noise. And if you highlight a certain frequency band, it'll show you exactly where that frequency is coming from. This is a super useful tool for looking at how things resonates through structures, looking at where your noise sources are. So this was cool. We had a lot of fun with this tool, but very useful for pointing exactly where the noise at 8 kilohertz was. What was the test equipment we used? So as I'm sure you could assume, we had the device under test. We had Brule and Care accelerometers. We had HBM current sensors. Unfortunately, we did not have an HBM torque transducer in this test. The next series will. We have a Genesis unit, so our eDrive system, where we were synchronously recording all the eDrive signals. We were viewing the signals live, so the efficiencies, the PWM voltages and currents, as well as frequencies live. And then we were taking the data out to BK Connect to do post-processing. So really powerful suite of tools we can offer. So the first test we did was efficiency mapping with vibration included. So what we did was we picked a given field current, so in this instance 3 amps, and we took a series of torque and speed points. So we set torque, we set speed, took a measurement, set torque, set speed, took a measurement, and to keep it simple, we used 12 measurements. And I have voltage and current in the blue and red, so voltage in blue, current in red. We can see we fixed voltage for a given set point, increased current. My speeds are difficult to see, but I have 1,000, 2,000, and 3,000 RPM with a torque that kind of goes up like this, and then efficiency points in the black. And these are just 1-second snippets of data that are spaced in time. And then I also had these accelerometers. So I only plotted 2. We had a total of 6. We can see that the accelerometer in one position had a relatively low vibration, and the accelerometer in the other position kind of increased with loading, as we would expect from based on the position. So again, this is pretty cool. And what we found was that the vibration was particularly bad with this field current at 2K RPM. And what this immediately gives us is the information to go, oh, as the controls guy, I might want to avoid 2K RPM at this field current. I might want to avoid this operation point. I might want to tune my control to fit this. And this gives you a really quick tool to go back to your NV guy and say, hey, I've got X vibration at 2K RPM. Is this bad? Or the NV guy might give you a spec that says you cannot go above 2K, go above a certain level of vibration for an operation point. So again, gives us ability to really quickly have just fast numbers and know if the control changes we're making significantly affect noise or vibration. Really cool feedback tool. Now, we traditionally make these efficiency plots. So up on the top screen here, I have my speed and RPM on the X. I've got torque on the Y, and I've got my spectral efficiency plot. And this was for the 12 points we took, and we kind of see this upward trend in efficiency, this really efficient point here. This is cool, but I also did this for the vibrations, where I took the same speed on the X, torque on the Y, and vibration in the Z, and we can see that while vibration increases with loading, it really is again stuck around that 2K RPM. And what we find is, at that really high efficiency point, we have a really high vibration. And this could be an issue for the engineers developing, the vehicle experience. And these might be things we want to watch out for. And it's a really nice way for guys who are used to looking at efficiency maps to also look at vibration. And again, this was just plotted in our software with our system. Pretty quick, easy, and it was just a couple of accelerometers. So ramps with efficiency. We also ran the typical NV tests where we set a torque in pink. We swept our speed in green up, held speed, and swept it down. We had 6 accelerometers, but we were also measuring voltage, so RMS voltage in the blue, RMS current in the red, and efficiency in the black. And a pretty straightforward test. We're going to see similar themes in common of increasing communication. We're going to understand how speed and loading affect vibration. And the electrical measurements now allow us to include, was it the control that affected this vibration? Was it the field current that affected this vibration? Give us more insight on what we're measuring. So on this graph, I have plotted spectrum of vibration for the 3 loading points on the top and spectrum of current for the 3 loading points on the bottom. And this is the full spectrum, so 50K hertz is in the Y, or excuse me, in the X. And we can see we've got that switching frequency around 10 kilohertz in both the vibration and current for all 3 graphs, and it gets increasingly strong in the high loading. We again see that field winding around 20 kilohertz, but we also start to see harmonic orders of those switching frequencies up around 40 kilohertz. So we get this really nice picture, and we can see that there's correlation between our vibration and our currents, which I think we could all assume. Oh, wrong direction. And then we can zoom in, and we can look at the fundamental, and we see the orders of vibration of our fundamental for the 3 loading points. And we can see it in our current as well. And we can see which orders or which harmonics actually have more significant content. And we can start to correlate between vibration and current, or vibration and voltage. And what I think is really interesting is if we look at the current spectrum, we see these fan blades coming out from 500 hertz. And honestly, we're not entirely sure what caused these, but they exist because they're in all 3 circumstances. And we can see some resonant bands right around 400 hertz and 600 hertz. And it really raises the question of, are these 2 things related? But we have the tools to start asking the questions and start root cause analyzing some of these issues. And we can see that, we've got this really, really nasty 5th harmonic in the higher level frequency range, or higher loading. So some cool stuff here. And just a way to maybe look at our currents, how the NV people would want to. Now, to cut to the meat of it, and Um, this is a plot where we actually took the spectrum of the inverter switching frequency and we looked at the voltage, and we can see that we have these harmonic bands in voltage that are from that PWM, those different size pulses. The voltage gives us these really nice, clean lines because the voltage is a very hard measurement. So the NV guys typically like to work in voltage, and it took a while to convince me of that, but I firmly believe it now. We have the current, which has this kind of diminished signal a little bit because it is a filtered version of the voltage. And then we have our acceleration. Um, and the really, oh, and then microphone. So these things are all correlated. But the really interesting part is that if we look at the bands themselves, we see that the weaker bands in acceleration correlate with the stronger bands in current. And the stronger bands in current correlate to the weaker bands in acceleration or vibration. Um, this also raises some questions of where are these resonances being excited, and what is doing the resonant excitation. So having the full picture gives us a lot of information for root cause analyzing problems. We can't just assume that the strongest current band is the strongest vibration band. It might be one of those lower order harmonics that's causing the larger vibration. So really cool stuff when you start looking at the full picture, from which other side of the fence you come from. Um, just a quick one on this. We plotted the ID and IQ, so the control currents, for one of these ramps tests. And while this test wasn't particularly interesting, if you start having uh, oscillations in your ID or IQ, you could directly correlate those control variables to something that's happening in, let's say, noise or vibration. Now, our ID and IQ are fairly stable in this test, so there's not much that's too terribly exciting here. But you can view these signals in real time. So if you start having an oscillation in let's say, your IQ, which is your current causing, or your torque causing current, and you start seeing an oscillation in your vibration, you could really make the effort to get a very accurate correlation of what's going on there. Or you could start to look at how it influences torque ripple. And when you start having all of these things, let's say you have an issue in vibration. If you want to go back to your group that's doing the electrical side, you can give them the full picture. You can say, I had a really bad vibration. Here's my torque. Here's my speed. Here's my field current. Here's my voltages and currents. Replicate it, fix it. This is your problem now. But it makes that communication consistent between groups. And then obviously I had to take things a step too far because I'm an engineer. I took that efficiency map from our first 12 points at the 3 amp field current, um, and I plotted it. And then I took those ramps tests, and I was measuring efficiency with my ramp tests. And I said, well, I should be able to plot this. And unfortunately, I only had ramp tests at 3 amp field current for 2,000 and 3,000 RPM. But when I plotted those, we could see very similar trends, and we see the low efficiency at a certain point as we increase the speed and loading. We have an increase in efficiency for my 2,000 RPM test on the bottom, or excuse me, my 13 Newton meter test on the bottom, and my 26 Newton meter test on the top. And as the NV engineer, if I run enough of these sweeps, I can really start to look at how my changes in noise and vibration affect the efficiency of the machine. And am I making drastic changes in efficiency? And then again, consistent data sets, increased communication, we can start to solve problems faster, increase the development time more quickly. So this is really cool, I think, because if you're running all these sweep tests, you can easily just take that efficiency data, dump it into an efficiency plot, and look and see, hey, am I drastically affecting the efficiency of the system? So it's cool stuff. It's really cool stuff, and it's going to speed up our development. It's going to make our jobs easier. So that's my spiel on noise and vibration. Increase communication, reduce capital costs. Let's all start speaking the same language. One last slide. Again, this was all done with our eDrive system, where we're measuring voltages, currents, accelerometers, microphones, but also CAN bus, temperature, and large numbers of signals. We have nice tools for integrating to test rigs, and a nice software for visualizing all these data. We can do a lot of calculations for power efficiency, but also NV. Uh, and very soon we're going to be coming out with some features for doing spectral plots live. We store all the data so you can do the harmonic analysis. So thank you for your time. I think I went a little longer than promised, but I hope you got some good information out of it.
Mitch, thank you so much. Well, you were on time. You were on time. That's okay. The
Wonderful.
most important thing is our attendees to listen to you and understand the possibilities, the eDrive possibilities, and I'm sure they liked it as much as I did. So I will conclude the webinar for only for the record because we will still have some questions from our attendees. So thank you all for participating. Don't forget to follow us on our social media on LinkedIn. You can find HBK there. And follow our web pages, check for the webinar pages, and register for more webinars. This is the February webinar week at which you can attend different areas and different topics, all of them interesting for you, I'm sure. Thank you all.